So now in this video, we come back to the circuit that I did a couple of videos ago, except for these components under my finger there weren't there before. Also, I have a higher value resistor right there right now. So this integrated circuit, there are 3 logic gates in there. You have to power it, positive, negative supply. And so there is a NAND gate over there, part of a NAND gate that also comes up there. And here is a NAND gate that we wired up. You should not leave the inputs floating like I am now, but it won't hurt anything, especially when you're just testing out circuits. So in any case, we have input, input, input right there. They're all to the negative supply, so we have a high output. It's connected to the positive supply as good as it can do. Since this is a 4000 series integrated circuit, this particular one, it really cannot provide much power. So I have 5 volts there, and let's actually, there we go. About 2 milliamps of current approximately. That's probably about the maximum it can output right now, but I'd like to get that red LED brighter. So we got this circuitry down here. Now this integrated circuit, and I have to set all the inputs high right there, other than right now this is floating. It's actually going high and low, rapidly picking up stray signals in the air. There we go. All the inputs have to be high for the output to be low. So right now the output's basically connected to ground. Blue LED lights up pretty good. So yeah, that is not too much of a problem, except for if we want more current to go through the LED so it's brighter, I have the overhead lamp at its lowest setting, so it looks, you know, a little bit brighter than it actually is because the camera adjusts. I'm also going to remove that resistor there, put 220 down here. So right now though, the circuitry, these transistors are off right now. They need a signal to the base to turn on. The left one is an NPN bipolar junction transistor. The right one is a PNP. So, in any case, there, you can see we got about 4 milliamps of current. That's very low. This is a 220 ohm resistor. I'm going to pluck the LED right there. And if I pluck the blue one, now nothing is connected to the output. And I'm going to grab a 10,000 ohm resistor and set it to the base of this transistor. So, this transistor is on fully. The LED is fully lit. You can see we got about 13 milliamps of current. So the output can't really provide the power we want to light the LED as bright as we want. But it has plenty of power to, you know, turn the transistor on. We just need a small trickle of current. A lot more current can go through the transistor. Now I'll take this 10K over here. And again, the output can't power the other LEDs and control these transistors at the same time. It has all kinds of problems. So I had to remove those LEDs. So now that jumper is just going to a blank row. It's not connected to those resistors. And yeah, now I can, we just need to get one of them off of the, it looks like floating. It does better. We just have to get couple of them off. Huh, that's interesting. Oh yeah, for we need all highs, that's what it is, for the output to be low. So there you can see the output of the integrated circuit. I had that messed up. So now they're all high, the output's low, the blue LED is lit over here, as you can see. Right now, this one's floating. It's bouncing high and low, so it's alternating which transistor turns on and off. If any of the inputs are absolutely low, then the output's going to be high right there. The main takeaway though was, let's look at how much current we want for the blue LED here. So yeah, this one's about the same. We have a 1000 ohm resistor there limiting the current. So the output can provide that for the blue LED. But since we got the transistors there, now we are jumping over. And what we are going to do now is we are going to replace these 220 ohm resistors with 1K resistors, so I can raise the voltage like I did in the last video where we had a lot of problems. So that should be a 1000 right there. Put the 220 and the other 1000. Hopefully that component doesn't short something. Didn't land where I wanted to. And we will pop this back this way. So since I got a 1000 ohm resistor now protecting the red LEDs. We will go back to red being there. Actually, I got to remove those for now. So yeah, we got a high output, and there you can see about 3 milliamps of current. That's because we're working with 5 volts. Now we're going to bump it up to 12 volts. And there you can see now we got about 11 milliamps of current because the transistor is on. Output is high, but a high output turns on the NPN bipolar junction transistor, so a red LED is lit up. And if that's kind of my goal, is to light the LEDs. So now I'm going to remove these resistors that turn the transistors on and off, and there you can see the power supply. It's it's providing current, but not enough to register on there. Less than 1 milliamp of current. And I'm going to put the resistors back. So I believe, what was that, 11 milliamps of current that we had before? That is when the transistor was on. The transistor was on fully. And here, oh, that's in the wrong spot right there. Need to go to the negative supply because the output's high. There we go. So 1000 ohm resistor. And there you can see it's only about 8 milliamps of current, where if instead we're switching the transistor, then we had 11 milliamps of current, even though the LED and the resistors are the same value. The output is just limited how much current it can output. It can do quite a bit more when you're at a higher voltage. Since we're using 1000 ohm resistors, 12 volts is where we're going to cut the limit. But there you can see the output is falling short of the 11 milliamps that it would want. So we're not getting the full 12 volts out. But with this transistor, when we turn this transistor on, then the resistor in the LED will see the full 12 volts, and you'll get the full current. So now I have my pocket oscilloscope. Each square going up is 1 volt right there, and it takes about 1 second for this to scroll across 1 square. So the alligator clip for the oscilloscope clip to this jumper, positive supply, and then the black clip to this jumper to the negative supply. So we got 5 volts. When I remove this, we'll get, who knows, there we go. We could get stray signals in the air or whatnot. But I'm going to go to the output, and you're going to see there, red LED is lit. The output is high, so it's as close to 5 volts as the output can get. Now, 555 timers and other single supply integrated circuits, they probably won't even be doing quite that close to 5 volts. But here you can see this is a rail-to-rail integrated circuit. So now we have the full 5 volts right there. I think it's rail-to-rail. We should be able to get ground probably while the LED is lit, I'm guessing. But in any case, usually it goes to ground better than the positive supply, but not always. And there you go. Let's tack that up there and put the red LED back. There you can see the voltage drop. So that is why the LED is not getting as much current as it could. We are getting the voltage drop. And there you can see we got about 2 milliamps of current, whereas with this LED it was higher. Let's remove this one and put the resistor and see what we get when we turn the switch on. So the switch will turn on fully, and so there you can see yeah, the voltage at the output didn't change. It changed a little bit, so even drawing that little bit of current, it dipped down a little bit. You may not notice that, but yeah, it looks like it's slightly more, but that's because we're only dealing with 5 volts. So let's go up to 12 volts, and this went off the screen. So what I'm going to do is instead of 1 volt per division, change it to 2 volts per division. So now it's 2, 4, 6, 8, 10, and it looks like it's 12 up there. And that is at the output. So it can still provide 12 volts. Now I'm going to remove this resistor. It did bump up slightly. So, you know, it dipped a little bit. But now we got the red LED. So again, it's about a square right there. Not quite a square, but each square now is 2 volts. So we're getting about 2, 4, 6, 8, 10, and you know, maybe 11 right there. But it was bumped up a little bit, so maybe 12 volts is up slightly. And I didn't, you know, try to get the line directly where we know for sure this bottom is 0. Looks like this is up a little bit. But in any case, there you can see it dropped down a little bit compared to what the supply voltage is. There it is up there. That's what it was down there, right there. So losing more than 1.5 volts, it looks like, at 12 volts right there. Now we will, that is an input that should not be floating around. Now what we're going to do, we are at the output, and as you can see, trying to power the load directly takes away some of the voltage. So if you want the full supply voltage across the load, in this case, it's much better to use the output to control the transistors right there. A high enough voltage above 0.7 volts turns on the NPN bipolar junction transistor fully. When it comes to the PNP bipolar junction transistor, it needs to fall about 0.7 volts, approximately 0.6, 0.7 volts below the positive supply. So anywhere from 0 volts up to almost the positive supply, but not quite positive supply. So what I'm going to do now is take 2 of these off, and remember, we're measuring the output there, and leave this one floating right there. And no, we're looking at the power supply. I thought we were looking at the output. There we go. Now we're looking at the output. So when this is floating, both of these look like they are on, but they are not both lit right now. One is lit and then the other one is lit, but it's going so fast that even looking in person, I can't see the difference. But there you can see the voltage jumping up and down until I give it a solid negative right there. So yeah, doesn't look like we're making it quite to ground, but you know, pretty close. Blue LED is lit up right there. So I'm going to do the same thing with the PNP bipolar junction transistor. Make sure I set it to the output, and there you can see that is lit up, but again, that LED is going to mess with the signal. So yeah, now we have the transistor on, and you can see it's getting much closer to ground right there. Let me put this directly to ground, and yeah, that's the problem. I didn't lower this line enough. So I can do that. I can press the button, I believe, and what is that? No, there we go. Press the division thing, and yeah, I can slide that up. So this is 0 volts, and I want to set it like right to the bottom for a more accurate reading right there. But we got a gist of what was going on, and yeah, that's really bright, that blue LED. Even though it's only 10 milliamps of current, as you can see there. Of course, I can turn the lamp on. That kind of washes it out. May make it a little harder to read that display or whatnot. So yeah, that's stuff I have to think about while I'm making videos. But in case you're thinking of making videos or something, thought I would point that out. So again, the output, it can, you know, power some loads, light loads, but we're already pushing it with these LEDs, where we are only asking, you know, for about 10 milliamps of current at 12 volts. And when we drop it down to 5 volts, it does change quite a bit with the voltage. It looks like, oops, went a little too far. Looks like at 5 volts, we're lucky to get 2 milliamps, maybe more. This isn't as accurate as a multimeter, but not terribly far off. If it says 2, it could be almost 3, you know, like very close to 3. It doesn't really seem to change to 3 unless it actually hits 3. Could be borderline. So maybe we can get like 3 milliamps out, but probably closer to 2 milliamps at like 5 volts. And then I'm thinking like 9 milliamps, like 8, 9 milliamps when you get up to 12 volts. So, in any case, I didn't explain this to be really easy for absolute beginners, but hopefully people that have studied electronics more found it more interesting. Let's get that off. I took off the LED, but this will get the positive coming in there to the emitter, and then the base will go through the resistor to the output right there if I left that resistor there. So yeah, now we completely cut off the current from this transistor. So again, this is a PNP over here. So it turns on when the output is low, and it delivers a positive to the LED so that it can light up. but the output has to be low. Here, the protective resistor is to the positive supply, and so the LED turns on when the output's low. It's connected to ground, and we looked at it with the oscilloscope. With the red LED there, that's connected to ground over there, the resistor. So when the output is high there, it lights up. But again, it doesn't make a terribly great connection, especially I think to the positive supply. I think it makes a better connection to ground, which is common with integrated circuits. Yeah, we saw we lost, a fair amount of voltage. It does have some useful power, but not much. Whereas with the transistor there, that same high output, instead of lighting the LED directly, turns the transistor on. So the current can go down to ground there, which makes the transistor connect collector to emitter to ground. So then ground comes to the bottom of the LED there, and it turns on fully. So the transistors, is very easy to turn them on fully. And I'll zoom in. So the transistors are facing each other. They are opposite polarities. So they have the opposite chemistry, but their pin layout is the same. So when it comes to the NPN, we got the collector on top, base in the middle, and emitter on the bottom. So pin layout is the same, but it's facing the opposite direction. So its emitter is on top, the base is in the middle, and then the collector is at the bottom. You notice that the emitter is for the PNP is to the positive, and this is a 2N3906. This is a 2N2222, but any NPN bipolar junction should work as long as it has the same pin layout. You can wire it the same. And so its emitter is going to the negative supply. They work the same, just polarities are opposite. You put the emitters, in this case because they're wired as switches, to the opposite supply voltage and the different input voltage. Almost ground will turn on the, a little bit above ground, I should say, will turn on the NPN bipolar junction transistor. It has to be high enough, whereas the voltage has to be low enough away from the positive supply. So down enough to turn on the PNP bipolar junction transistors. Opposite polarities right there. I can wire them both at the same time as long as I give each one their own resistor right there. So when the output is low, that one will be on, and then if I add this one over here, so although these LEDs at the output do kind of interfere, so there you can see, yeah, the blue one didn't turn off unless I get rid of these LEDs. Now, without those throwing off the voltage, now we can solidly get just the NPN bipolar junction transistor on, and it's holding the PNP off, and we have to get all inputs high because it's a NAND gate. So it's the opposite of an AND gate. AND gate, all inputs have to be high for the output to be high. This is the opposite. All inputs have to be high. I believe I said that wrong. For the output to be low. It's the NAND gate. It's not and, it's the opposite. Again, this just building simple circuits like this. As you learn more about transistors, integrated circuits, inputs, outputs, and all that. These little simple circuits there, they are not practical circuits. You wouldn't really use it in any real life application. But wiring this up helps you get familiar with all the components, which does make it easier to wire up real life applications. I just don't have any real life applications to think of right now. But if you want to accomplish something, you just think of all the components you know how to use, and generally you'll figure out how to put together the ones you need to put together to get the outcome that you want. And I mostly like making videos, though. Hopefully people find the circuits interesting. That's my goal for making the videos. Try to get a circuit that I think you'll find interesting to learn about. But you have to go from there to build circuits that you'll think is practical, or modify other circuits or something. But in any case, rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.